Hello everyone, welcome to class number 5. What are we going to do today? Okay, today is class number 5. In this class number 5, we will discuss how to code vectors. Matrices. What else? Um, Random numbers. So today we are doing some very important sections of our lecture series. So this is actually these vectors and matrices are the core areas of numerical analysis, which we want to focus on, and which we should know actually how to code from Python. So this is without further ado, we go directly to discuss vectors and matrices. So topic is, let me write it on the LaTeX format, vectors and matrices. We have already discussed the data structure called list. We can use a list to generate vectors and matrices. How do we do that? Let's say I have test 1 equals a list where the entries are 1, 2, 3. Okay, now the list 1, 2, 3 is stored in the variable test1. Print type test1. We know that it's a list. Okay. Instead of using lists, the better way to do this is the use of NumPy arrays. Okay. Let's say test2. First, I need to import the NumPy module to this. So I should import NumPy as np. So I import the NumPy module and I abbreviate it as np. So I don't have to write NumPy all the times I'm using the NumPy module. So you will see how it's done. So I only have to use the np. So let me call second variable test2 equals, instead of writing numpy dot array, instead of writing this, I can just write np dot array. np dot array one comma 2 comma 3. Okay. Print type test 2. Now, this is the type of this test 2 array is it's called the NumPy ND arrays. So the type is different from a list. So this is a NumPy array. So vectors can be written in two ways. One is the list way and the NumPy ND array. So if you use NumPy ND arrays, there are many operations and tools for us to manipulate the vectors and matrices. Okay, let's move on with the vectors. Let's focus more on vectors. Vector. Vectors. They are one-dimensional arrays. Okay. How to write a row vector? Row vector. How do I write a row vector? Let's say my row vector A equals np dot array. One, two, four, five. Print A. Okay, 1, 2, 4, 5. Now this looks like a vector, doesn't it? From our mathematics knowledge. In mathematics, we usually, let's say, mathematics, we usually call a vector a column vector. 1, 2, 4, 5. This is the usual way of writing a vector. If we want the row vector, we get the transpose of it. The rows become columns and columns become rows. 1, 2, 4, 5. So in Python, this is the way we define a row vector. So we get a row vector. Not a problem. Okay. Next, the type of A. We know that it's a NumPy ND array. Print A dot shape. We want to check the shape or the dimension of the vector A. Number of dimensions. Or yeah, number of dimensions. Wait a second. Okay, let me run this code to see what happens. Okay, it shows some 4 comma something. 4 comma nothing actually. what is happening here? Now this vector A is equal to, we know that it's a row vector, 1, 2, 4, 5. According to the principles of linear algebra, how do we write the shape or the order of the matrix, order of the vector? It is 1 into number of rows is 1 and number of columns is 1, 2, 3, 4. So we write this as 1, comma 4. This is the dimension of the vector. So, but for some reason in Python, it shows 4, uh, 4, in this format. I don't know what the reason is. But the correct way of doing it is this one. I'm a little skeptical about this. Why Python does something like this. Anyway, just keep that in mind. We can move on. Print a dot size. What print a dot size. What will it print? Number of entries or number of elements. So how many entries are here? 1, 2, 3, 4. 4 entries are here. So it should print, when I run this code, it should print 4. Okay. Print A0. Just like the list, this is the way we are accessing the first element of the vector. How does it happen? We know that the indices, what are the indices? This is the 0th index. This is the first index, second index, and third index. So accessing the first element means accessing the 0th index, which means what is at the 0th index? The entry 1. So this should print 1 here. Okay. Next, column vector. B equals np dot array within square brackets. We should write the individual rows like this. This is one row, this is a row, and this is another row, and this is another row, and this is another row. So let's say I want to write this vector A, no, sorry, vector B. Vector B equals 1, 2, 4, 5. Now this is a column vector. How many rows are here? 1, 2, 3, 4. So order is 4 into how many columns? 1. This is it. Now we write individual rows in these square brackets. So this is row. First row is 1, second row is 2, third row is 4, fourth row is 5. So we defined the column vector. Now let us see if it is coded correctly. Print B. Yeah, it's correct. Print B dot shape. Oh, this is the order of the matrix or order of the vector. And vector is a matrix, so it is all right for us to call it a matrix, not a problem. So this gives us the correct data, like 4, comma 1, like this one here. Now Python um, gives us the row order of the column vectors correctly, but it gives us order of the row vectors. It gives us that wrongly. So I don't know what the reason is. Maybe someone should check it, or we should inform to the developers. Anyway, next, print p dot size number of elements of the matrix. And we know that 4 elements are here. 1, 2, 3, 4. So okay. Next function. Next we are going to learn the arange function. Function arange. Function arange could be used to generate vectors by specifying start, comma, stop, comma, and comma, step. Function arange could be used to generate vectors by specifying start, stop, and step. You may not understand it now. Let's look at it. Let's have a look at it with an example. So 1 to 10 vector, 1 to 10 vector, 1 to 10 vector equals np dot. Instead of array, we write a range 1, comma 11. So this is the start, and this is the stop. The step size is not specified. Actually, the step size is 1 here. So when the step size is 1, we don't have to separately mention it. So Now we can print 1 to 10 vector. See, starting value is 1, step size is 1, and it goes all the way to 10, because the stopping value is 11, which means it stops one step ahead of that. So that is fine. So we, unlike the unlike the array function, in the range function, we don't have to write all the entries in the array here. So we can use the arrange by specifying start, stop, and step to generate linearly spaced vectors. So that's an easy way to go. Next is another function link space. Function link space could be used to generate linearly spaced vectors. Let's see what it means. Y equals np.lin space 1,100. So in the arrange function, we wrote the start and stop, and if we don't specify the step, it takes the step as 1. However, here it does not necessarily take the step as 1. We'll see. See, now it now the gap between first entry and the second entry is not 1. So we can clearly see the step size is not 1. And how many entries are here? How do we check that? Which function do we use to check that? Can use size. Y dot size 50. In the linspace function, in its usual form, in its normal form, it generates 50 entries. But if we want 100 entries, what do we do? Or any number of entries, how do we specify the number of entries? Let's say z equals np.lin space 1, 100, we want 100 entries, 100 linearly spaced elements. Okay. Now it looks like we got 100 elements here, because it goes at a step of 1, 1, 2, 3, 4, 5, 6, and so on and so forth, up to 100. It looks like we've got 100 entries. Let's check z dot size. 100. So that's fine. We'll go to the next section, matrices. There are 2D arrays, two-dimensional arrays. Let me define my first vector. So first matrix in P dot array. We define it in the same way as the vectors. Within square brackets, we write within square brackets, we write the rows with another square brackets. Right? This is the first row, second row, third row. In the first row, we separate the entries with commas. 1, 2, 3. In the next row entries are 4, -5, 6. In the next row, the row entries are 5, -6, 7. Okay, something went wrong. 5, -6, 7. We can save it. Can see if it is saved correctly. Yeah. So this is the first row printed here. 1, 2, 3. Second row, 4, -5, 6. 4, -5, 6. Third row, 5, -6, 7. 5, -6, 7. No problem. Print a dot shape. So our matrix is 1, 2, 3, 4, -5, 6, 5, -6, 7. Number of rows is 3. Number of columns is 3. So this is a 3 by 3 matrix. So this is the shape or the order. This should print 3 by 3. Print a dot size. This should print the number of entries in the matrix. How many entries are here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 entries are here. So it should print 9. Next. How do we access the element in the second row and third column? How do we access the element in the second row, which means this row, and the third column, this column? How do we access this entry? Second row is this, third column is this entry. How do we access this entry? We have to write the correct indices. Print A Now, what are the indices? Row indices. The first row is the index number 0. Second row is the index number 1. Third row is the index number 2. First column is index number 0. Second column is index number 2. Third column is second column is index number 1. Third column is index number 2. So this element is at, or this entry is at index row comma column index 1 comma 2 index. This is at 1 comma 2 index. So we write a square bracket 1 comma 2. So we should access this entry, which is 6. 6. Next is the subtopic generalizing matrices. np.ones this gives values of 1 to each element in matrix. I will bring examples for these statements so you don't have to worry about them. Gives values of 1 to each element in matrix. NP zeros use values of 0 to each element in the matrix. np.I gives an identity matrix. np.random.rand gives random values to each element in the matrix. NP random random. Use random integer values to each element in the matrix. Random integer values to each element in the matrix. Okay, let's put them into practice now. So print, I want to get a unity matrix. NP dot ones 5. So okay, what went wrong here? Okay, NP ones use values of 1 to each element in the matrix. So we will get here a vector. A vector that has 5 entries and all the entries are ones, like this. Okay, can you predict what this will give? NP B equals NP dot ones 3 comma 1, 3 comma 1. Print B. Now this will generate a 3 comma 1 matrix. What's a 3 comma 1 matrix? 3 rows and 1 column. All the entries are ones because we are using the ones function here. So this is the. So this should print. Like that. Next, C equals NP ones, NP dot ones, equals NP ones, within bracket, 2 comma 3. Print C. What will this give? It will give us a matrix that has 2 rows and 3 columns. 3 columns and all the entries are ones. 1, 1, 1, 1, 1, 1. So this should print. See, now we notice here that here it does not print as once, exactly once, but 1 dot, like 1 dot something, 1.0. Like here 1.0, here 1.0, here 1.0, 1.0, 1.0, 1.0. So it prints floating point numbers, not integers. What if we want integers, not floating point numbers? So we can define C as C equals np dot ones within bracket 2 comma 3 outside the first bracket decimal type d type equals integers int. Now this actually right by d type integer by d type equals integer, all the values get converted to integers. And see. Now see, now these are not floating point numbers, these are integers. No decimal point is here. Okay. And the next one, let's say C equals np dot zeros. Zeros within brackets 2 comma 3, say d type equals integers. What will this print? Earlier we printed ones for all entries. Here we print zeros for all entries for a matrix with same size or same order, 2 comma 3. D type, decimal type is integers. Print C. See, all the entries are 0. The size, the shape of the matrix is 2 comma 3. Decimal type is 0 because we don't find the decimal point here. So the type, decimal type is integers. Okay. And the next one, how to print identity matrix. Print np dot identity matrix. Okay. This will print a 3 by 3 identity matrix. See, 3 by 3 identity matrix. By identity matrix in linear algebra, what an identity matrix is, a square matrix. A square matrix is a matrix that has same number of rows and columns. So the identity matrix is a square matrix that has diagonal values of ones, main diagonal values of 1, and all the other values are 0. This upper triangular values and lower triangular values are 0. The main diagonal values are 1. So that's an identity matrix. This is an identity matrix of 3 by 3, and this has decimal types, the floating point numbers, because we see decimal point here. You see decimal point. So what do we do about it? Like if we want integers only, print np dot identity matrix 3 comma d type equals integer. Okay, that's how we get integers. Next is the next subsection. What is that? Random numbers. Generating random numbers. Okay. D equals np dot random dot rand. So this is the random number generating function, random and rand, and this will create a vector that has 5 entries. All the entries are random numbers between 0 and 1. Int D. We have 5 entries in the row vector. 1, 2, 3, 4, 5. And all the entries are random numbers between 0 and 1. So what do we do to get any random number? We multiply it by 10 or 100 or whatever. Let's say we want to get a random number between 0 and 1000. So we multiply all the elements by 1000. So not a problem. So it is important that we know how to get a random number between 0 and 1. The next is d equals np.random np.random dot rand 3 comma 2. What will be what will we be getting? We'll get a matrix that has 3 rows and 2 columns. And all the entries in the matrix are random numbers between 0 and 1. Okay, next random integers. Let's say I want to get, let's say this code d equals np dot random dot randint 1 comma 100 in d. With this randint function, in this randint function, we specify the limits of the random number we are going to get. It's like this. From this code, we get a random integer between 1 and 100. Okay? 5. If we run it again, 42, 99. So we get a number between 1 and 100, an integer number, randomly. D equals np.random dot randint 1 comma 100 comma in range D. So this will generate a vector that has 10 entries. All the entries are random numbers between 1 and 100. Here we got a vector that has 10 entries and the entries are between 1 and 100. Okay. How about the next one? Retrieving elements from a matrix. Next section, retrieving elements from a matrix. Let's say my matrix is x equals np.array. I write the rows 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, 10, 11, 12, 9, 10, 11, 12, 13, 14, 15, 16, 13, 14, 15, 16. Print x. Okay. First row, second row, third row, fourth row. Okay, it is correct. Next, print x dot shape. What is the shape of the matrix or the order of the matrix? We know that it's 4 by 4. So it should print that. The next one, access element in the third row and fourth column. Third row and fourth column. Print x square bracket. What are the indices? What is the index of third row? This is the first row, second row, third row. Index 0, 1, 2, 3. Index 0, 1, 2, 3. So the third row is index number 2. Index number 2. And fourth column is index number 3. Index number 2, index number 3. The entry is 12. So it should print 12. So we want to access the element in the third row and fourth column. It should print 12. Okay. Access third row, the whole row. How do we access the third row? Entirely print x square brackets. As I said, the third row is index number 2. Let me write it here. Okay, this is index 0, 1, 2, 3. Index 0, 1, 2, 3. Access third row. We know that the third row is index number 2, and we want which column? We want all the columns. So we write the colon mark, colon symbol to denote we want all the columns. So this should print 9, 10, 11, 12. So we will see if that happens. Then 2, comma, colon. 9, 10, 11, 12. No problem. Access fourth column. Print X. What is the fourth column? The fourth column is this column. Fourth column is this column. So, so in the Englishes we write the to the right side we write the index of the column, which is 3. The fourth column, index of fourth column is 3. Index of the row, we want all the rows. Here, all the rows. So all the rows and fourth column, this column. So this should print 4, 8, 12, 16. So we'll see if that happens. Yes. That's how we retrieve elements from a matrix. Next subsection, submatrix. But submatrix is the view of the original matrix. The view of the original. Let's see what it is with an example. C equals np dot array, np dot array. We'll get the same X as before. This one. Okay, now we define Y Okay. We define y to be a part of x, like define y is the part of x where the rows are 1 through 3, comma, the columns are 1 through 3. What does that mean? Let us find out now our x is okay. Now we define our y to be part of x where the rows are 1 through 3. This is the index 0, 1, 2, 3, 0, 1, 2, 3. 1, this means 1, 2, excluding 3. Indices, the row indices are 1 and 2. The column indices are again 1 and 2. So we project this. We project this. So this is the part of x we are considering. We are taking as y. 6, 7, 10, 11. So that is what we have got here. 6. The y is 6, 7, 10, 11. Y. So we now set all the elements, all the rows and all the columns of y to 0. Now we see what has happened to y. 25. Now the entries are set to 0. Now the values in y are all 0. Now we feel like nothing has happened to x because we changed only y. But is that the case? We'll see what happened to x, int x. The middle part of x, which is y, has become 0, all zeros. So in fact here y is a view of the original matrix, not a copy. If y was a copy, then nothing would have happened to x. So in these instances, when we want a copy, not a view, we need to use some other function to make it a copy. Okay. Note, if any change is made to y, then the corresponding change happens in x. original matrix X gets deformed. Gets altered. When we need a copy, not a view, how do we get that? Let's say X is the same. Y equals this part of X dot, dot copy brackets. Okay. Now we set the entries of Y to 0. And Y. Now that Y is a copy, nothing should happen to X. The X remains the same. Middle part has not been changed. Good. Here, X remains the same. Okay. Next is the reshape function. The next section, reshape. Let's say we consider the same X. Okay, that is not a problem. Uh, um, Now this is how we define rows in a NumPy array. So these are the rows. Instead of doing that, if we have a row vector, how do we reshape the entries into some other matrix where it has a different order or different shape? So we'll see. So print np.arange np.arange 1,17. Now this should print this should give us a vector that has 16 entries, going from 1, 2, 3 up to 16. Like this. We want to reshape this. We want to reshape this into some other shape. Let's say now that we have 16 entries, we can reshape it to 4, 4 matrix that has 4 rows and 4 columns. Let's see if it can do that. Yes, it can. So we created the matrix X with some other way. So that's good. We can use it, we can apply it in certain instances. The next example, print np.arange 12. So this should create a row vector starting from 0 to 11. Number of entries are 12 because 0 is included. So we have 12 entries here. We want to reshape this into, now that we have 12 entries, I want to reshape it to 3, 4 shape. Okay, 3 rows and 4 columns. Correct. Next example, print np.random.rand. You make 12 random numbers and please reshape it to, now that I have 12 numbers, I can reshape it to 3, 4 maybe. No, 4, 3. Just to make a difference here. So 4 rows and 3 columns, all of them are random numbers. Yeah, correct. That's good. Next is some fancy indexing part. So let's have a look at it. A equals np.linspace 0, 1, 11. So this will generate 11 numbers ranging from 0 and 1, including 0 and 1. So it will create a vector. This vector. So the gap between two consecutive numbers is 0.1. Okay. Print check values in A that are greater than 0.5. So this checks values. Now we know that which values in A that are greater than 0.5. Only these values. 0.6, 0.7, 0.8, 0.9, 1. 5 numbers are greater than 0.5. So the last 5 are greater than 0.5. As they are greater than 0.5, when we check this condition, it prints as true. All the other values for all the other values, it prints as false because they are not greater than 0.5. Print the values of A in such a way that this condition is satisfied. Only the values that satisfy this condition should print. So this asks me to give the values only, values in which indices, in the indices that are satisfying this condition. So these are the values that satisfy this condition. Okay. So that's fancy indexing. Next is another section, amending the matrix. Let's say my matrix is np.arrange, np.array, no, arrange, np.arrange 1, 17. I have 16 numbers. I reshape it to 4x4 matrix. Print x. Print okay, that's fine. X 0, 0. The 0th element. What is the 0th element? This one. First row, first column element, which is 1. So we replace it by 10. Now we print x to see what has happened. So the very first element should be replaced with 10. X. All the rows and the second column that has the index of 1. Those values are replaced with 2. So which means all the rows and second column. All the rows and second column. Index number 1 column. This column. We set all the values to 2. So this one we make it to 2. Make it to 2, make it to 2, make it to 2. Index. See, the corresponding change has happened. Next one, X. The row index 3, which is the 4th row, and all the columns values should be set to 3. index. What will that what will that do? Row number 3. Row index 3, which means this row 0, 1, 2, 3, and all the columns. So all these entries should be replaced with 3. So yes, correct. That change has happened. Next, all the rows and all the columns values are replaced with 0. Print X. Yeah, predictable. Okay. So that's how we amend the matrix. That's how we make changes to a matrix. The next is concatenating matrices. Matrices. Okay, I have to write a couple of matrices here. np.array within square brackets, rows 1, 2, 3. No, 3 is enough. So this is my first matrix, second matrix, third matrix, fourth matrix. B, C, D. Entries are 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, 2, 1, 6, 5, 4, 6, 5, 4, 9, 8, 7. 2, 1, 3, 2, 1, 3. 5, 4, 6. 8, 7, 9. 2, 3, 1. 5, 6, 4. 8, 9, 7. Yeah, I have my 4 matrices here. Now, what if I write this code? Print np.concatenate. np.concatenate within bracket, A matrix and B matrix. Concatenate, it will concatenate two matrices row-wise. Okay. So what happened here? We have our first matrix A and the next matrix B, and they are combined to make a single matrix with A matrix on top of the B matrix. Yeah. So that's how we combine matrices. So this is how we concatenate two matrices row-wise. Row-wise meaning um, the first matrix A, the rows of first matrix is they are on top of the rows of the B matrix. So that's what it means. That's fine. So the same thing can be achieved with the V stack function. Print np dot v stack within bracket a comma b. So it's the same thing. I think the vstack command, vstack function is very short and easy to use. Now, earlier we concatenated two matrices row-wise. How about we want to do it column-wise? That means the columns of the A matrix um, first, and then columns of the B matrix should be printed to the right of the columns of A matrix. Print in P dot concatenate A comma B axis equals 0, axis equals 1. Concatenate two matrices column wise. Matrices column wise. So you see, this is the A matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. B is printed to the right of the A matrix 3, 2, 1, 6, 5, 4, 9, 8, 7. The same thing can be achieved with the H stack function. And P dot H stack A comma B in bracket within bracket A comma B. Okay, next I'll give you an exercise. Try this. Try this and see if you can do this. Exercise. Print matrices according to below order. Matrices A and C should be horizontally align, and D and D are below them. So how can I get this? Yeah, like this. Combine them into one single matrix. Combine all four of these matrices into one single matrix in such a way that A, C, B, D should be in this order. A, C are on top of the BD, and A to left of the C, and B to left of D. So we can first try to concatenate the top matrices A and C horizontally. NP dot H stack horizontally stack, which two matrices A comma C. Okay, now this is a combined matrix of A and C. Okay. We also want to, how do we do this? Let me call this matrix E. Let's say my matrix F is, I want to horizontally stack the matrices B and D. This is B comma D. Okay. Then I want to vertically stack these two combined matrices E and F. NP dot, let's say it's G, NP dot V stack. E and F. E comma F. Print G. Okay, this is the A matrix. This is the A, fine. This is the B. This is the C. This is the D. So yeah, this is all these are correctly stacked into one single matrix. This actually we can call this the method 1, because we can do the same thing in some other method 2, in some shorter method where we can actually do everything together. Like we can print the G matrix by concatenating E and F together, like NP dot. We want to vertically stack V stack what? E and F. E comma F. Instead of writing E and F, we write this one and this one without further steps. So with a single step, we calculate, we actually create the whole matrix G. We print G. Yes, yes, it's correctly done. Print E dot shape, sorry, not E, G dot shape. We can see that this is a 6x6 matrix. So we should see it 6x6. The size, how many entries are here? 6 multiplied by 6, 36. Print G dot size. 36. Okay, that is all I wanted to do in the class number 5. We actually did a lot of things today. So I hope you enjoyed this and I hope you will find this useful in your applications. So we have 2 more classes to go, class number 6 and class number 7. In the class number 6, I will do some matrix operations and how to plot graph. So that's an important section. In the class number 7, I will do some machine learning example and how we can do some simple machine learning exercise with the um, modules available in scikit-learn website. So that will be something enjoyable. Okay, I think that's it. Okay, see you guys.